Okay, hi everybody, welcome to our review of momentum. So today's going to hopefully be kind of quick and, oh, my computer's kind of freaking out. What I really want to do is just review our momentum ideas and go over it. So what I'll do is a quick little lecture. Hopefully this goes quickly. This is just for Friday. Usually I like to stretch it for the 2 days because we end on Friday, and then Monday you guys don't have to do anything and I get to like plan stuff. I don't know what's going on. But so today's just going to be a quick lecture, and if it goes quickly, then I'll give you some practice questions, some like more multiple choice style questions. If it doesn't go quickly, then I'll be like, oh, I gave them too much, just watch this video. So that's what we're doing, and hopefully I'll go quick and I can give you a few quick questions, but I don't want to like overwhelm you for one day. So before, what we were talking about is we were talking about conservation of energy, and we had these situations where we were able to analyze the situation through this conservation of energy. We had one single object. It would interact with the environment, or it would interact, just kind of change on its own. It would go from some height to some lower height, or it would roll down a ramp or something. But we were really focused on one object. And conservation of energy is perfect for when we have one object. This conservation of energy is this law of the universe. It works, it holds up, and it's really helpful. It helped us analyze a single object in a system. But this idea of conservation of energy, it gets a lot harder if we have more than just one object in our system. If we have multiple objects in our system that are interacting with each other and their velocities are changing, then it gets tricky. Then we need something else to help us analyze what the heck is going on here. And when we have these objects interacting with each other, what we're going to call that, when we have these two objects that collide with each other or undergo some sort of brief interaction, we're going to call this a collision. So when objects collide with each other, that's a very common thing. That's something that we see a lot in the real world. Typically, we don't have just a single object doing a single thing like falling or whatever. When we want to analyze more complicated situations, typically that involves multiple objects. So it's common for these objects to undergo a collision, and this collision, we're just going to define it as a brief interaction between two objects. And all collisions are different. And the properties of these collisions are really based on the property of the material of our colliding objects and their ability to compress with each other. So it may not look like it, but when objects collide, there's this brief little compression. We'll talk about why this happens in a moment, but the compression really changes up our type of collision. So really quickly, I just have 4 examples to show you. Slow-mo guys, again, I show you videos from them all the time, but I think they're just awesome, especially to see this physics happening in real time. So here we have this balloon, it's filled up with paint, it hits the guy, it kind of swings down as a pendulum. We have this collision between the balloon and the guy. And we see that when this happens, this balloon is filled with paint, this balloon, it like compresses, that paint all kind of squishes together, and he feels that force starts to kind of move him, but we have this nice little like compression. We have this, I guess we'll watch him fall backwards because it's kind of cool, but we have this compression of the paint in there. So that force is kind of spread out over a longer period of time. The next one I have is we got this 4-ton wrecking ball hitting the side of a car. Here we see, okay, hits the side of the car. The wrecking ball itself, it like doesn't compress at all. It's a very rigid material. It doesn't compress. But we see the door, it kind of starts to crumple. So we have this crumpling of the door. This force, again, is happening over some sort of time. We have this crumpling. Come on. Another example, I like this one a lot. This guy puts his tongue in the mousetrap. So you see, okay, it clamps down his tongue, it's gross. When this is happening, again, this force is happening over some amount of time. So yeah, it happens really quickly, but you see that doesn't compress right away. It's happening over a duration of time. I think that's really cool and also super gross. Let's see, just keep going. Show me more. There we go. So yeah, so it took some time for his tongue to compress. So kind of cool. And then the last one I think is kind of neat. We have him doing a flip and compresses that balloon. It's filled with water. And I try to hit full screen, and it didn't give it to me. That's okay. So we see, oh, there we go. This force is happening over some duration of time. And really what's going to define our collision is how much force we have and how much time it takes for that collision to happen. So yeah, let's look back here. here. So we have this idea that all objects are going to compress. And really what's going to define our collision, like I just said, is how much these things compress, so how much time it really takes for this collision to happen. So we talked before when we were looking at Newton's second laws, or just Newton's laws in general, we said that objects, if we zoom in at a microscopic scale, really all that objects are is just a bunch of atoms arranged in a certain configuration. And these atoms are held in place by these chemical bonds. And if we want to kind of create this model that helps us think about what's going on, we can think about these chemical bonds as just springs. So these atoms are kind of in this fixed position. They're where they want to be, but they can still compress, get a little bit closer to each other. When that happens, though, they want to stretch back out, so they're back at this equilibrium position. If they stretch, then they say, okay, well, I want to compress back so I can be back at this equilibrium position. So these bonds are acting just like springs. They can compress, stretch, and they're really what causes forces. And if we think about this in a collision, we can think about different objects having different strengths to these chemical bonds, just like how different springs have different spring constants. Some springs are easier to compress, some springs are harder to compress. So if we have a more rigid material, the springs, these chemical bonds, are going to be harder to compress. Or if we have kind of a more flowing material, something that's a little bit looser, those bonds are going to be a little bit weaker and they're going to be able to compress more. So the microscopic properties are going to determine how much an object can compress. But if we think about them like springs, we know that we have this Hooke's law, this spring equation for the force of a spring. It's based on the spring constant and then the amount of compression. That's what tells us how much force we have. So if we're thinking about these objects colliding with each other, if we have kind of more compression, or if we have more force, then we'll have more compression of our objects. And maybe that'll take more time depending on the material of our object. But pretty much main idea, we have this compression and the force is playing into the compression. So how much compression we have is going to be based on how much force we have and also the property of our materials. But if we're thinking about why this compression actually matters, if we zoom in at this microscopic level, when objects collide with each other, they're going to provide a force on each other. If we have one object over here, another object over here, they'll kind of compress each other's springs, compress those chemical bonds. We're going to have this force. These objects are going to force each other. And when we have this force from a collision, we can call this an impulsive force. You don't need to know that definition, but it's just kind of, hey, we can call this an impulsive force. And what we can do is we can graph this impulsive force. We said, okay, this force is happening over some amount of time. It takes some amount of time for this spring to compress. We have this force, and we can create a graph of this force versus time graph. And the force versus time graph, it looks something like this. We know that a spring, the force is based on how much we stretch or compress our object. So we won't have the same amount of force immediately because while this force is happening, we see the amount of compression changes. Like if we look at that balloon example, at first the balloon was pretty much its nice balloon shape, and then it started to compress more over time. So it doesn't reach this maximum compression right away, so it's not at this maximum force right away. So this force is really changing over time. And I have a quick little PhET simulation. This isn't the best because it doesn't happen in like real time, but if we look at it, the spring's not just going to like instantly reach its maximum force, right? If we are compressing it, if we're thinking about this object as being made up of a bunch of tiny little springs essentially, it doesn't reach the maximum right away. If we look at this graph, I guess you can't see where I'm pointing, but if we look at this graph, we have to go through this range of forces before we reach the maximum. But so this is going to happen at some sort of rate. It's not going to happen instantaneously. So we're going to typically get this nice kind of like bell curve, not quite a bell curve, but this nice little curve. It says, okay, at first it'll kind of stretch out. Then when it reaches the maximum, we'll slow down. And then it'll stretch back like that. It'll be like, hey, I want to reform. I want to go back to this shape that my bonds want to be at. I want to be back at this equilibrium position. So we can kind of see that with our shape right here. So we have that compression begin. So where our spring was not stretched, then it starts to stretch more. We have the maximum, and then it stretches back out, back to its equilibrium. And why this force versus time matters is because the area under the force versus time graph is going to show us a few things. It's going to show us the effect of the impulsive force, whatever. It's going to show us the impulse. Again, kind of a weird term. But really what it shows us is the change in momentum. So the impulse is the change in momentum. So it's showing us what is this force doing? How is it changing the momentum of my object? And then one quick little thing too. What we're more used to with our equations is we're kind of saying, well, yeah, this force is changing throughout time because objects are like springs and we have this compression that's happening over time, so we have this force changing over time. But what we're usually going to do, for the most part, when we're actually plugging into equations, is we would say, well, instead of looking at this full curve, that's a hard area to calculate. So let's just kind of say, oh, well, the average force is about this, and it's spread out over some time. So let's just say that the total area is just the average force times this change in time. So usually if we have to calculate something, we'll just be doing the average force times time, or if it gives you a value of impulse, it'll say, oh, the force is a singular value happening for this amount of time. So usually if you are finding the area directly, or if you're calculating impulse, it'll tell you, oh, the force is just this. It's giving you the average force, because finding this changing force and doing that, the whole curve, that requires us doing integrals, and it's difficult. So we're not going to do that. We're just going to say, oh, well, yeah, the average is this. Or it'll give you something nice and smooth and kind of approximate it as a triangle that you can calculate. But so if we're looking at all those examples from the beginning, we said every object is going to be different. Every object is going to collide in a different way, and it'll have different degrees of compression. So why does that matter? Why does that change? So in this case, both of these curves are going to have the same amount of area. They have the same area underneath. They have the same impulse. So our objects are going to have the same change in momentum. But really what's different here is we have different amounts of force. And this kind of determines so much about our physical world and what we see and what we notice and what we experience when we have collisions. So if our force happens over a longer amount of time, we can get the same amount of area as if our force is happening over a short amount of time, but we kind of have to minimize and maximize things and kind of balance these out. So if our force is happening over a longer period of time, that means our force can be lower. Here we see this force peaks out at about, I don't know, what is this, like 17? So we have a lower force if we spread it out over a longer amount of time. If our force happens quickly in a short amount of time, then we have a higher force to have that same change in momentum. So if we think about the two kind of like wrecking ball examples, if we have the person kind of being hit by that ball or that balloon filled with paint as like a pendulum or a wrecking ball, that force was spread out over a longer amount of time. That force, that the paintball was really able to compress, so that force happened over a longer amount of time, so the force was lowered. If we think about the 4-ton ball, the wrecking ball, that doesn't compress very much. So if that hit the person, we'd have a lot of force happening over a short period of time. They'd have to have the same change in momentum because they both come to a stop. They have different masses, so it's a little bit weird. But they both have to come to a stop, so their momentum has to change. But if it doesn't compress as much, we're going to have more force in a shorter amount of time because that compression isn't happening as much. It's harder to compress, so that can't spread it out over that period of time. That's why we saw that car door. It definitely like compressed a bunch. It definitely bent it. So we want to build cars that can crumple a little bit because we can increase the time of that collision and therefore decrease the force and still have the same change in momentum. So these graphs are huge, and they're huge for kind of dictating how the world works and what makes collisions safe or unsafe, and it's cool. But so we've talked about impulse, and we kind of defined it as this change in momentum. We're just going to pretend we've never heard of it before. So what happens when you force something? When you force something, we know that Newton's second law tells us that the object is going to accelerate, which means that our object is going to change velocity. So here we're seeing these two objects forcing each other. They have this impulsive force, and they change their velocity. They have this force, therefore an acceleration, therefore the velocity is going to change. So again, pretending we've never heard of momentum, we've never got an equation for momentum before, what we can say is if you kind of take your nice, maybe backwards Nike shoe with your stick figure leg and you kick a ball, you're going to apply some force, and we can use Newton's second law to say our force is going to equal the mass times the acceleration. And let's just plug in for average acceleration. Our average acceleration is our change in velocity over our change in time, and we can rewrite that as v final minus v initial. That's just what a change is, final minus initial. Then we can kind of move things around a little bit and sub that in. Instead of acceleration, let's plug in our v final minus v initial over our change in time. So we replace this for acceleration. We can move things around a little bit and say our f average times our change in time is equal to mv final minus mv initial. And if we notice this, we said, oh, well, this force average times change in time, that's what we defined as our impulse or our change in momentum. And here we have mv final minus mv initial. So we have a final quantity minus an initial quantity, or initial minus final. So we have this change of this quantity. So we can say, oh, well, this momentum can be quantified as this mass times velocity. So that's just kind of where that equation comes from. Impulse is our force over this time, and we can use Newton's second law to argue that that equals our mv final minus mv initial, this change in this quantity being momentum. So if we want to define momentum, if we want to put a definition to it, it's kind of hard to just define, honestly. It's kind of hard to get a good definition for. But what it is a conserved quantity that's associated with the motion of an object, and it's the product of the object's mass and its velocity. So if we have a lot of mass, we have a lot of momentum. If we have a lot of velocity, then we have a lot of momentum. And one thing that's really important when we talk about momentum is it's the velocity. So when we have velocity, that means the direction that it's moving, that matters. So we have to define momentum as either being positive or negative. So here we have our equation for momentum. This P stands for momentum equals mass times velocity. There's those little arrows on the top to indicate these are vectors. The direction that they're going matters. We have to have positive momentum or negative momentum. That is very important, especially when we're looking at these conserved cases. So then what we said before is we said, okay, well, the impulse is really just the change in momentum. So we can get this equation too, where we say, hey, this force times change in time, that stands for our impulse, our change in momentum. So this force times our change in time is our change in momentum, this delta P, so delta being the change. And one of the main things that we are going to use momentum for is this main idea that momentum is conserved. So if we consider two objects that are colliding with each other, we have to look at this collision and say everything about this collision still has to satisfy Newton's laws of motion. They still have to apply. We still have this collision where force is happening. So let's look at this and kind of define conservation of momentum or derive it from this idea that Newton's laws have to apply anytime we have these objects interacting with each other. So let's say we have object 1 and object 2. They have this crash course. They're going to collide into each other. And when they collide into each other, we said, okay, well, they're going to interact with each other, and this interaction is going to be a force. And what we know about Newton's third law is, well, one, it still has to apply, and Newton's third law tells us that we have this equal and opposite reaction. So if we look at this, we can say, okay, well, object 1 has a force acting on it by object 2. And then object 2 has this force acting on it by object 1. And we know Newton's third law tells us these have to be equal and opposite to each other. So negative force on 1 by 2 is equal to positive force on 2 by 1. These forces have the same magnitude to each other, but they're happening in different directions. And because we have this force acting on these objects, in this case we're showing, oh, well, they have this acceleration, they have this change in velocity. In this case, they went from having this, if we look at just 1, had a positive velocity, and then it has a negative velocity. It had this change in velocity. 2 was going to the left and then to the right, so it went from a negative velocity to a positive velocity. It had this force acting on it, which caused this acceleration. And this idea of these forces being equal and opposite is huge. So if we're looking at force and impulse and this change in momentum, we can say, well, our impulse was this force happening over some change in time. We know that this time that object 1 is interacting with object 2 is the same time as object 2 is interacting with object 1. So the amount of time that these two are in contact with each other has to be the same, right? That just physically, it wouldn't make any sense if object 1 was touching object 2 for longer than object 2 was touching object 1. Whenever they're in contact with each other, they're in contact with each other. We can't change the amount of time that they're in contact with each other. They have to be the same. So delta t is the same. We said negative force on 1 by 2 is equal to positive force on 2 by 1. And then what we can do is just kind of multiply both sides by this delta t and say negative force on 1 by 2 times delta t equals force on 2 by 1 times delta t. And we have this idea, we said, well, force times delta t is our change in momentum. So we can say the negative change in momentum of 1 equals the positive change in momentum of 2. We just kind of carried that sign through because, again, sign matters. So this is huge. This is telling us the momentum gained by 2, so this positive change in momentum for 2, equals the momentum lost by 1. Here we have this negative sign, so we have this lost momentum for object 1 is equal to the gained momentum by object 2. This tells us we use Newton's third law to show that momentum is conserved. When we have this closed system, we see momentum is conserved. So that's a huge idea. Instead of just being like, yes, it's conserved. Here's where it comes from. It comes from the third law. So conservation of momentum, huge idea. We're saying in a system, momentum is going to be conserved. So the system is the same as when we talked about it in energy. The system we define as what we care about. Everything else that's not part of the system, we're going to say it's the environment. And one main idea, one really important thing when we're defining the system with momentum, is that if we have internal forces that act within the system, then energy is conserved. So if all the forces within the system, within this collision, are internal, then momentum is conserved. If we have an external force, then we say, okay, these forces are coming from the outside of our system, momentum is no longer conserved. Then we have this situation where we have an increase in momentum to the system or decrease, and then we no longer have this conservation. But if we define our system to be everything that's forcing each other, then we can say, okay, if all the forces are happening within the system, then we know that momentum is going to be conserved. So kind of I bolded it, main idea, if there are no external forces, the total momentum within the system is conserved. So it's kind of like in energy. When we only analyze what was happening in the system and we have everything going on in the system and all the changes happening in the system, we said energy was conserved. As soon as we have an outside force doing work on our system, energy is no longer conserved. We're either adding energy or taking away energy. Same thing here with momentum. If we have everything internal, all the forces are happening between the objects in the system, then momentum is conserved. If we have something outside of our system doing a force, then momentum is no longer conserved. So when we want to solve problems, it's kind of nice because all these momentum problems are going to follow the same exact format. What we have to do is we have to define the system, and we're going to want to choose a system. If we do get to choose a system with no external forces. So sometimes we won't be able to choose it, but if we can choose a system where there's no external forces, that'll be huge because we know that momentum will be conserved. Then what we want to do is draw a picture of the system before the collision and after the collision. So we can think about what was happening before, what was happening after. Then we can determine the momentum of each object before the collision and add them to find the total initial momentum. So the initial momentum, this conserved quantity, this initial and final momentum, is made up of the total momentum of all of our objects. So if we have two objects, we have to find the momentum of one and the momentum of the other, add them up, that'll be our total momentum. Then do the same thing later. So determine the momentum of each object after the collision and add them to find the total final momentum. We know that if there's no external forces, the total initial momentum has to equal the total final momentum, and then we can use that idea, this equality, to solve for any unknowns. And we also have to remember that signs are super important. If we have something moving in the negative direction, we have to define that as a negative momentum. So let's try one out really quick. So let's say I have cart number 1 is moving to the right towards cart number 2. Cart number 1 has a mass of 26 kilograms and an initial velocity of 4 meters per second. Cart number 2 has a mass of 6 kilograms and it's not moving. These two, they collide with each other and they stick. So we have then they're moving at some final velocity that we want to solve for. So we drew our picture, and now let's kind of set up a table of before and after to help us out. I like to list all my objects on the left and say, okay, well, I have mass 1, mass 2, and then the total system. So let's plug in what we know. We know that the velocity of cart 1 initially is 4 meters per second, so we can find its momentum. We can do P equals m times v. So we have a momentum initial of cart 1 of 104 kilogram meters per second. Kilogram meters per second being our unit for momentum. For cart number 2, it's not moving at the beginning, so it has a velocity of 0, which means it has no momentum. So the total initial momentum equals 104 kilogram meters per second. If that's the total initial momentum, that has to equal our total final momentum. So we can say our total final momentum is also 104 kilogram meters per second, and that's made up of the two carts moving. This mass of cart 1 moving at some final velocity, and this mass of cart 2 moving at some final velocity. So we can say, okay, we have momentum of cart 1, momentum of cart 2. We can add them up and set them equal to this 104 kilogram meters per second. So we can say 26 VF plus 4 VF is equal to 104. 30 VF equals 104. VF is equal to 3.46 meters per second. So we can figure out the final velocity after this collision. One thing to keep in mind is that because these two objects were stuck together, we can say, well, they have the same velocity because they're moving together. That may not always be the case, but if we have our objects sticking together, they'll have the same velocity because they have to be moving at the same speed. So then just kind of to wrap things up, we want to be able to define different types of collisions. The ones that don't matter really, like to actually have a formal definition for them, an explosion collision, this is a situation where we start with zero momentum and then the objects explode away from each other and they cancel out each other's momentum. So we'd have something moving to the right, canceling out the momentum of something going to the left. And this is a situation where we start with no momentum and we end with no momentum. So that's an explosion collision. An inelastic collision is a type of collision where kinetic energy is not conserved. When we talked about inelastic collisions, we were mainly focused on a perfectly inelastic collision. So one where our objects will stick together. So we just had this example here where our carts stuck together. That's an example of a perfectly inelastic collision. So inelastic, if we want to think about a good definition of it, really the definition is going to be a collision where kinetic energy is not conserved. And then the one that we care about, the one that they kind of make a focus on with the College Board, is an elastic collision. So elastic collision. This is a type of collision where kinetic energy is conserved. And when we see this, the objects will bounce away from each other. They will elastically bounce from each other. So if something asks us, hey, is this collision elastic or inelastic? We would have to check and see, was the total initial kinetic energy equal to the total final kinetic energy? So elastic is a type of collision where kinetic energy is conserved. Any other type is just going to be an inelastic collision if kinetic energy is not conserved. And then, so we said momentum is not conserved. If an external force interacts with the system, then momentum is not conserved. In that case, we'd have to say, hey, how much impulse did we add to the system? And we'd have to incorporate that into our equation. And then one last little thing. This is something that I kind of skipped the first time we do momentum. I like to save it for the review because before that we hadn't really talked about center of mass. When we started to talk about rotation, that's where we talked. This is my rotation symbol, I don't know. But when we talked about rotation, that's where we defined the center of mass of an object. Because we said, okay, like objects will balance at their center of mass. If you're forcing them away from the center of mass, that's where you get a rotation. So the center of mass is kind of where we can think about all of the mass being concentrated, where we could balance an object. So remember we had that little bird thing. If you held it right by the beak, that's where the center of mass is. If you support that center of mass, you will have your object balanced. So we have a center of mass for systems as well. If we have a system of objects, then they also have a center of mass, even if they're not connected to each other. So that's a weird idea, but even if they're not connected, they still have a center of mass. So what we can pretend is, to like help us think about this a little bit, is we can pretend there's a very thin invisible rod that's connecting these two masses. So if we have this invisible rod connecting mass 1 and mass 2, if mass 1 is 1 kilogram, mass 2 is 2 kilograms, think about where you'd put your finger so that you could balance these two rods. Like where would that be? Would you put it closer to mass 1 or closer to mass 2? So hopefully this is pretty intuitive to you. You've balanced stuff before. So where would you put it? Make a little prediction, maybe yell it at your computer, I don't know, whatever you want to do. But where would you put your fingers so that you could balance these things? Well, we know based on our experiences in real life, we'd want to put that, we'd want to balance it closer to object number 2, closer to the heavier one. So one thing that AP Physics 1 wants us to do is kind of be able to identify where qualitatively would the center of mass be. And the reason that we care about center of mass for a system is because, well, one, all systems have a center of mass. And when objects in a system collide, the velocity of the center of mass will not change unless there's an external force on the system. I'm going to say that one more time because one, it's important, and two, I kind of butchered it. So when objects in a system collide, the velocity of the center of mass of the system will not change unless an external force is exerted on the system. So I have a little simulation that'll show that. So that idea is important, and really one thing that the College Board wants us to do, one thing that they ask questions about, is kind of having this idea where you're saying, okay, they want you to be able to predict the velocity of the center of mass of a system where there's no interaction outside of the system, but there's an interaction within the system. So they want you to just say, hey, if we have a momentum, if we have conservation of momentum, if we have a collision, the center of mass, the velocity of the center of mass will stay the same before and after the collision. So that's a really weird idea, but I think this visual is really helpful. So if we think about, switch over here, having a collision, this X is going to denote the center of mass. So whenever we have a collision, just kind of watch the center of mass before and after. So before it's moving with this kind of slow velocity, afterwards, even after this collision, the center of mass is staying with the same velocity. So no matter what we have, restart this. No matter what kind of collision we have, the center of mass is going to stay with the same velocity before and after a collision. So we see this little x is staying the same. So that's kind of an idea that for some reason the College Board, they want to kind of, like, I don't know if they want us to know, but saying one more time, the center of mass before and after a collision, the velocity of the center of mass before and after the collision is always going to be constant. It's always going to move with a constant velocity. The velocity of the center of mass is going to be constant before and after a collision. So yeah, that's all I got for our quick little momentum review. Hopefully quick. I don't know how long this took.